I try to share my screen. Okay, now you can see it. So the first question, it led me to prove the Markov inequality from the negative continuous random variable. And here's my procedure for the first question. I first write Ex equals to the integral from -infinity to +infinity. This is X is a negative, I can also integrate from 0 to +infinity. And for any negative real number a, Ex is greater than the integral from a to +infinity. And furthermore, I substitute X equals to a, and the inequality still holds. After I expanding the term, Ex is bigger than a times the probability of X is bigger than a. So after rearranging the term, Px bigger than a is smaller than the expectation of X divided by a. That finished the proofs of the first question. Now comes to the second question. Second question asked me to show that the Sn squared is converged to sigma squared in probability. So by Markov inequality, this inequality holds. So by the definition of mean squared error, this expectation equals to the variance of Sn squared plus this term. Okay, so the variance squared is equal to this one, and I related the variance squared to the variance of Sn minus 1 squared. And by the result of the third question, which I will prove later. So the variance Sn squared is equal to this one. And since the expectation of the x to the power of 4 is finite by the Jensen inequality, which I will prove later, the mu4 and the sigma to the power of 4 is also finite. So after substitute this into the expectation of this term, I get the limit of Esn squared is equal to the sigma squared. So by the sandwich theorem, this inequality holds. So the limit is going to 0. So which is finished the proof of Sn squared converges in probability to sigma squared. And here is the Jensen inequality to prove that any higher finite moments implies the all lower moments are also finite. So this is the question 3. Question number the first problem of the question number 3 is quite straightforward, I think. So I want to prove the expectation of Sn minus 1 squared is equal to the sigma squared. I expand the Sn minus 1 squared to this. So because the samples are identically distributed, so covariance is equal to the n1 divided by n times variance x1 times the variance of xi. So after rearranging the term, I got the expectation of Sn minus 1 squared is equal to the sigma squared, which finishes the proof. And the second problem of the question. Wait a minute. So this is the second problem of the third question. Variance S squared is equal to this one, the expectation of x to the power of 4 minus the square of the expectation of x squared. So all we need to do is to fix out the expectation of x to the power of 4 in the second problem. I use a little trick here. Note random variable y is equal to x minus the expectation of x, and the variance of y is equal to the sample variance of y is equal to the sample variance of x. And so I just expand all the term. Actually, I just expand the term out and get the n-1, and the square root of n-1 times x to the power 4 is equal to is equal to these three terms. And I just figure these three terms out one by one. The first term, I expand it out, and by the assumption of identical distributed, I use the covariance equals to 0, and to figure out this term is equal to this term is equal to this term, and this term is just the sample variance of y, which is also the sample variance of x, so equal to the sigma to the power of 4. And I just figure out the first term, and the second term is here. The second term and the third term, is actually is basically obeying the same the same progress of expanding the first term, which I have explicitly write the progress here, and I will omit the explanation. And after I figure out the second term and the third term, I rearranging this term and I figure out the expectation of the x to the power of 4. Then I substitute the expectation of x to the power of 4 back to the original expression, and I got the variance of the sample variance. So which finishes the proof. And the fourth question is just obeying the large n cases without assumption of normal distribution. This expression, this expression after a normal, this expression under large n cases is basically obeying the normal distribution, and I use the R term, and I use the R software to figure out the Q norm. So after plugging the Q norm into J alpha divided by 2, I figured out the 97% approximated confidence interval. So that's all the explanation of these 4 problems. Thank you.